A loop moving through a magnetic field. A rectangular metallic loop of dimensions L and W, and resistance R moves with constant speed V, so this is constant speed V, to the right as shown in the figure. So this is moving inside this uniform magnetic field. The loop passes through a uniform magnetic field directed into the page and extending a distance 3W. So the distance here is 3W, 3 times the width of this loop. About the x-axis, along the x-axis. Define x as the position of the right side of the loop along the x-axis. So this is our x-axis. Part A, plot the magnetic flux through the area enclosed by the loop as a function of x. Part B, plot the induced motional EMF in the loop as a function of x. And part C, plot the external applied force necessary to counter the magnetic force and keep V constant as a function of x. So let's start with the magnetic flux B when x is between 0 and W. So remember that x equals 0 is the position of the right side of the loop. So the right side of the loop is here. When x is equal to 0, this loop is completely outside the magnetic flux, outside the magnetic field. And it enters the loop. It's going to have an increasing magnetic flux, and when it is into the loop by an amount x here, we will see that L times x will be the area. So L times x will be the area that's inside the loop. So it's going to be BLX. So once again, when x is equal to 0, the flux is 0. When we have this loop into this area by an amount x, so let's call this distance x here. So that's inside the loop. Okay, so I can note that here. This is basically, this distance is x, that's inside the magnetic field, and therefore the magnetic flux in this region will be Lx, the area, multiplied by the magnetic field, BLX. Now, when it is completely inside, it's going to be BLW. You can see that all of the area will be inside this magnetic field. It will be BLW. So when x is in between W and 4W, this is going to be actually 3W. This is going to be completely inside. So when x is equal to 3W, we will have the right side touching the end of this region. So it's going to be basically BLW for all of this scenario. So all of the area will be inside the magnetic field. So it's going to be BLW. When x is greater than 3W but less than 4W. When it is 4W, the right side will be a distance W from the end of this region. So that means all of the loop will be outside. So at 4W, it has to be 0. So it's going to be decreasing from BLW. The magnetic flux will be minus BL x minus 3W. When x is equal to 3W, the flux is BLW. When x is equal to 4W, it's going to be BLW minus BLW 0. When x is greater or equal to 4W, the magnetic flux will be 0. So if we plot this here, you can see when x is equal to 0, we are completely outside this region, so flux is 0. X is between 0 and W, we have an increasing flux. When x is W, we are completely inside this magnetic field region, so it's going to be BLW magnetic flux. When x is equal to 3W, the right side is touching the end of this region, and afterwards it starts decreasing until 4W, when it's going to be completely outside again, and then we have 0 flux. So this will be the answer to part A. Okay, now if we look at the induced motional EMF in the loop as a function of x, the induced EMF is epsilon equals minus d phi b dt. It's the rate of change of magnetic flux. So here's our magnetic flux again. So if you look at the ratio, if you look at the derivative with respect to time here, since this is moving with a constant speed, the rate of change of magnetic flux for x between 0 and W will be basically the derivative of this minus BL dx dt, and outside that region for x less than 0 it is 0. So here we have epsilon equals 0, and here we have epsilon equals minus BL dx dt, so that is minus the derivative of this. Then we have the derivative of BLW, which is going to correspond to 0 induced EMF. Between 3W and 4W, if I take the derivative of this, derivative of BLW is 0, derivative of BL3W is 0, minus BLX, derivative becomes plus BL dx dt with the minus sign for induced EMF. So here epsilon will be equal to BL dx dt, and outside x greater than 4W we will have 0. So this is going to be basically dx dt is v, because it's moving with constant speed v. We will have 0 induced EMF for x between minus infinity to 0. 0 to W we have minus BL dx dt minus BLV. W to 3W is 0, 3W to 4W is plus BL dx dt plus BLV, and then afterwards it's 0 again. So that's the answer to part B. Now, in part C, plot the external applied force necessary to counter the magnetic force and keeping V constant. So, the applied force will be equal to I L cross B, which is ILB, and the current flowing through this is going to be epsilon induced EMF divided by the resistance R. So we will see that the applied force should be P square L square V divided by R. Now, when we are entering this region, entering the constant speed V, the velocity V points to the right. Now we're going to have this rectangular loop LW going into this region. So you can see the velocity V points to the right. We are entering this region of uniform magnetic field. So what is the direction of the induced current? Well, the induced current will be opposing this increasing flux into the page, which means the current should be flowing counterclockwise. Using the right-hand rule, if you follow the current direction with your forefingers, the thumb points perpendicular to the page in the out of the page direction. So this should be the induced current direction, creating a magnetic field, induced magnetic field, that's opposing the magnetic field into the page. So this is the magnetic field into the page, and that's the induced magnetic field. Okay. Now, the term L cross B, for the top and the bottom, if we consider the top and the bottom, because the current is flowing in opposite directions, L cross B and L cross B, the top and bottom will cancel each other. So we will have top and bottom L cross B, total value of L cross B is equal to 0. Now, so the contribution will come from the right-hand side here. The left is not inside the magnetic field. The right-hand side basically has this induced current flowing in this direction. So if you follow the current direction and curl your forefingers into the page, the thumb points to the left, which is telling us that the applied force FB must be pointing to the left. So this is our this is the force that will be felt by the wire. So as the magnetic flux into the wire is increasing, IL cross B basically points to the left. That is the force due to this magnetic field. Therefore, the applied force should be pointing to the right. Applied force should be pointing to the right, and it's going to be in magnitude equal to B square L square V over R. Okay, so because we have IL cross B, remember this side is L, this is going to be ILB, and this side has no contribution, it's not inside the magnetic field. Top and bottom, the magnetic forces will cancel each other when they for the portions that are inside the magnetic field, and therefore this contribution will come from the right side, which will be a magnetic force pointing to the left, requiring an applied force to the right to keep V constant. Now, as we are exiting this region of constant, of uniform magnetic field, again the velocity points to the right, we will have the following scenario. Now, this is the end of the region, and therefore the magnetic flux into the page is decreasing. So we have to create an induced current should flow in a direction that is going to produce a magnetic flux into the page. That is basically in the clockwise direction, so that if you have your right hand thumb pointing in the direction of the current, forefingers inside the rectangular loop will point into the page. So this is going to create an induced magnetic field into the page. And if you follow the L cross B, so this direction of this current is the direction of the L vector. L cross B is now pointing to the left. That's the direction of the magnetic force, which means the applied force should be pointing to the right again in order to keep the velocity constant. So the current direction, induced current direction, is found using Lenz's law, and we see that both during entrance and exit, the magnetic force Fb points to the left. Therefore, the applied force should be pointing to the right. F applied points to the right in order to keep the the speed constant. Now, in between omega and 3 omega, when x is in between omega and 3 omega, the induced current in this loop is 0, I is equal to 0. Since epsilon is equal to 0, therefore the magnetic force is equal to 0. So this magnetic force should be positive, pointing to the right, both during entrance and exit, and it should be equal to b square L square V over R. And so you can see it's in 0 and W, it's b square L square V over R. 3W to 4W during the exit, it is b square L square V over R, and otherwise it's going to be 0. And this applied force is directed to the right in order to oppose the magnetic force acting to the left. Okay, so in this example we have a loop moving through a magnetic field with constant speed v moving to the right. It has resistance R, dimensions L and W. Now, for the magnetic flux as a function of x, where x is defined as the position of the right side of the loop. When the right side of the loop position x is 0, we're outside, so the magnetic flux is 0. When it is W, we're completely inside. It's going to be BLW, B times the area. For it into the, when this is, if this is basically our origin, if it's inside the loop by an amount x, x times L will be the area inside, so that will be the area inside. So BLX will be the flux. Until when? Until x is equal to W, it's going to be BLW. Afterwards, the flux is constant, it's BLW until x is equal to 3W, where the right side touches the end of this region, and afterwards it's going to start decreasing until x is equal to 4W, when it's completely outside the loop. When x is equal to 4W, here you can see BL 4W minus 3W. BLW, BLW, they cancel, we have 0 flux. So x greater or equal to 4W is going to be 0 because we're outside this region of uniform magnetic field. The induced EMF, motional EMF, is minus d phi b dt, so it's minus BL dx dt, so it's minus BLV in this region. The derivative is 0 here, it's 0 here, and it's going to be derivative of this is 0, derivative of this is 0, minus minus plus BL dx dt plus BLV when it is in between 3W and 4W, and otherwise it's going to be 0. So here it's 0 minus BLV 0 plus BLV 0, so that's what we see here. Now, for the external applied force necessary to counter the magnetic force and keep V constant, first of all, I have to find when we are entering this region for this loop, where is the magnetic force coming from? The magnetic force on a straight wire of length L is IL cross B. The I is the induced current. So first task is to find the direction of the induced current. If the magnetic flux into the page is increasing, the four fingers, when it follows counterclockwise direction, we see a magnetic field inside that is pointing out of the page, perpendicular to the page. So this opposes the increasing flux into the page. So that's the direction of the induced current. Now IL cross B, well, here the magnetic field is 0, here the magnetic field is 0. For the top and bottom, if you look at L cross B on the top and L cross B at the bottom, you will see that the magnetic forces will be canceling each other. So the only contribution, non-zero contribution, comes from the right side, where L cross B, the direction of the current is pointing up, four fingers point in the up direction, curl towards the magnetic field into the page, the thumb points to the left, the magnetic force is to the left, the applied force should be to the right to oppose the magnetic force and to keep V constant so that the acceleration is 0. What is this applied force? It is ILB, where L is the length of this side, so it's L. And I is epsilon divided by R, so it is basically since epsilon was BLV, it is B square L square V over R. That's the magnitude of the force. And it's pointing to the right. When we are exiting, the magnetic force we're going to feel will be due to the left side of this wire. Now it's induced current will be producing a magnetic flux into the page because the flux into the page is decreasing. That means the current flow should be a clockwise direction. So four fingers curl in the direction of the current, the thumb points into the page, that's the induced magnetic field. So IL cross B points to the left. So that's the magnetic force. That means the applied force should be pointing to the right. It has the same magnitude, B square L square V over R. So the magnetic force is positive, directed to the right, B square L square V over R, applied force. For x between 0 and w, 3w and 4w, in between what happens? The induced current is 0 since the EMF is 0, which means the magnetic force is 0. Therefore, we don't need any applied force in this region.